In this question, we want to use the cylindrical shell to find the volume of the solid obtained by rotating the region about x-axis, everyone. Okay. Since it is x-axis, it means that we have to write everything in terms of y and take the integral with respect to y. What's the visualization here? How do we visualize this object? X is equal to y squared. Then x is equal to 0. Y is 2, y is 5. Okay, it makes my life much more easier because it gives me a boundary for my y. It says, hey, y is bounded between 2 and 5. So I already have the lower bound and upper bound for my integral. So let's graph this guy. If you try to graph this, y squared is equal to x, basically you have y equals to square root of x and y equals to negative square root of x. Okay, take square root of both sides, but don't forget the signs, everybody. Let's take a look at this. My y is equal to square root of x. Down here, I have y equals to negative square root of x. Or basically this guy representing x equals to y squared. If it's more comfortable writing it that way, then you have x equal to 0, which is your y-axis. This is x equal to 0. And it says, hey, you have two horizontal lines as well. Y is equal to 2. So when y is 2, x becomes 4. Okay, and then y equals to 5, x becomes 25. Okay, that's how we get these. So let me just graph it this way. Y is 2, and then y is 5. So what are we trying to get? This is the region that you're to rotate about your x-axis. So you can erase the rest of the things. Perfect. So let me erase these. I don't need these. Just make it more distracting. Now we have a nicer object. We don't need this part as well. Okay, perfect. So I have the following happening here. Due to symmetry, you can just use everything on the other side if it's easier. So here you have this guy, and this is the object. Not a perfect visualization, but you get the idea what's going on here. Then to show that we actually have a 3D object, we use these dotted lines to show that, hey, we actually rotate this object along this. Perfect. So now, since the question says use the cylindrical shell method, let us take a typical shell, cylindrical shell, and this guy is located here. For example, it has a base which is located on y-axis, and its height, okay, shouldn't have moved that up, but that's fine. Let's see. Get the general idea of what's going on here. This is a typical cylinder. It has a base and it has a height. The height is just right here, right? So I'm going to rewrite this function as x equals to y squared, because when I calculate the height is the maximum x value, which is y squared, minus the minimum x value, which is down here, 0. So this is your height, right? We just rewrote it this way so we can graph and visualize this a little bit easier. The height is bounded between maximum x value, maximum x, and the minimum x. So this is your height. Remember that the volume of rotation using the shell method is the circumference, but the circumference down here depends on y, right? This is your y, starting from 0 to a typical y value. So the radius is bounded between 0 and y, right? So you can write down r equals to y. So here you have your circumference, which is 2 pi r or 2 pi y times the height, which is y squared minus 0. Then you take the integral with respect to y. And you already know that your y is bounded between 2 and 5. So you have the upper bound and lower bound. The rest is just calculation. The volume is the definite integral of 2 pi y times y squared dy, or 2 pi divided by 4, y to the fourth, and then you have 2 to 5. Let us plug in 5, then plug in 2, pi over 2 of 5 to the power 4 minus 16. So if you multiply 25 by itself, let me see. 125, hopefully, if I'm not mistaken. Let me use my calculator. 625. Okay, pi divided by 2. 625 minus 16. So if we do the subtraction, and divided by 2, you get 609 pi divided by 2, which is the volume of this object that we rotated about x-axis using the shell method.